Hello, class. We are having our lecture on Kirchoffs Law and series versus parallel resistors. We're moving through chapter 2. Really chapters 1 and 2 were the beginning, and get your real engineering dimensions and units down. Sort of have a understanding of the power equation, and let's just write the power equation up here. P equals VI, right? So P equals VI, and also V equals IR. Right? I snuck that right in there. So those are our two equations. That looks horrible. Just there we go. Those are our two equations that we had from the last lecture, and I'm not sure if I could fit anything else into this lecture. We'll see how it all goes. That's quite a bit to put into a lecture anyway. So let's see what we have. Now, Kirchoffs Law. Basically, let's just draw a circuit. And this is going to be a little more complicated circuit than we had last time. I'm still going to use our symbol for a DC power source. And we'll decide what that is in a little while. But let's put some resistors and stuff in there. I have a resistor here that's in series with another resistor. And then uh, maybe we could have a resistor that's in going down here, and then we've got another resistor and another resistor and another resistor all in series that come back along here. Then I'm going to throw in one more resistor in series with that parallel resistance that we have down here. Right, so we've got a lot of resistors there. Let's label those resistors. That'll be R1, R2, R3, R4, R5, R6, and R7. Whoa, that is a pretty complicated little circuit to have on your fifth lecture, isn't it? Let me get another colored pen and we can just sort of look at what's going on here, right? What is really going on with this whole circuit? Because this is what Kirchoffs law is telling us in a nutshell. Now I'm going to, just a second, I'm going to give this a number. Let's just give this some numbers. Let's say that this is 100 volts DC. I'm just using a large DC voltage like that because, the resistors I'm going to use are resistors that now are going to start to fall into the resistances that you are going to see as electrical engineers, and you get out there and you start using a variety of different resistors. Resistors have nominal values. And we're going to do a lab on that where we look at the various different ways to, read a resistor and what the resistor values are and all of that. That's actually your first lab. I may have already assigned that to you. You may have already done that even before getting here. But I haven't done that lab before I've done this lecture. So really, let's get this lecture out of the way. So if that's 100 volts, let's say that we've got out of all of these resistors, let's come up with some. I'm just doing this off the top of my head, by the way, and that's why I have my handy calculator here. That's a 40-year-old calculator. I think I got that like 40 years ago. It's actually a notation by, it's a Radio Shack calculator. Yeah, that was from 83. So that's almost 40 years ago. But that calculator has a very strange notation. I call it reverse alien notation. You may have heard of Hewlett Packard has reverse Polish notation. Well, this one has like reverse alien notation, but I certainly know how to use it. And it's not going to help anybody else. All right, now let's go into this. So let's say R1 is just 100 ohms, right? We know that that's just a standard thing. And R2, I'm going to say, is 120 ohms. R3, we might want to keep that as sort of a standoff resistor so that not a lot of current flows through here and more current is going to flow through here. So, I'm going to say that R3 is 680 ohms. And then R4 is 270 ohms. R5 is going to be, let's say 330 ohms. R6, I think I'll put another, well, we don't want to confuse things, do we? So 180 ohms. R7 is, well, we don't want R7 to be too high, really, but we want it to be high enough. So I'm going to say that that's 390 ohms. All right. So that's our little circuit that we're going to try to work our way through using Kirchoffs laws and using the fact of series and parallel resistances. So to prepare us for this, because you can see that I've really got things in series here, right? And what we've got to do to find out, what we really want to find out is what is the current that's coming out of this power supply. It's 100 volts DC, but what's the current that's coming out of that power supply and then flowing through the circuit? This first current here I'm going to call I, just call that I, because that's really the main current flowing out of the power supply. In the end, and that's what Kirchhoff tells us, is in the end, I have to have the same amount of I, I'm going to put that down here, coming back in, right? But what happens right here? What happens right at this spot? Right at that node? Let's actually, I think everybody can, well, I'll put a little circle around. What happens at that node, that bullseye that we've got right there? Yeah, it's got a name, and it's called a node. You want to get the electrical engineering terminology down so that you know how to speak engineering. And so right there is a node. So I come out of here. This is not really a node. This is just part of my schematic drawing, isn't it? Because you can see that right there, I don't have current that could go anywhere else. Current goes in that. You could say that's a node, but current's going in here and it's coming out here, right? So if you want to call that a node, sure. But it's only going in one way and it's coming out one way. So it's pretty, it's sort of the null case if you wanted to think of it as a node. When you look down here, I think you can see this also is a node where I've got current that's coming in and I've got current that's going out. Now let's examine these two nodes that I've got here. I'm going to give those nodes a name. I'm going to say that this is node A and this is node B. All right? Now, let's redraw those over here, those two nodes. So if I've got node A, right, that's node A. In fact, I'll just put this node, I'll use my node that I wrote down there to do that. Now node A. Now let's look at the current that's flowing into node A and the current that's flowing out of node A. Well, we can see right on top here that the current that's flowing into node A is coming in this direction. And then if it's flowing in, it only has two ways to get out. It can either go out this way, or it can go out this way. Now, if we say that the current that's flowing into node A is I, then let's say that the current that's flowing out of node A this way is going to be I sub Z. Okay? And I'm going to call this I sub W. And I think that you can see if we were to do, because we can neither create nor destroy current, right? Current is just charge flow. So we have to have the same amount of current coming out as we've got going in. So if I did a summation equation, I would say that I, the current flowing in, has to equal I sub W plus I sub Z, right? Does everybody see that? That just makes sense. And that's what Kirchhoff said. Kirchhoff said if I can take any node, the current, and we could even say that about that node, couldn't we? The same current going in, current going out. Current going in, current going out, it's pretty boring. Whereas this node is interesting because we don't know how much of the current, let's say that there's 1 amp of current flowing in. Well, if 1 amp of current is flowing in, then is half of an amp flowing out through I sub W, and half an amp flowing out through I sub Z, or is 3/4 flowing out through I sub W and 1/4 flowing out through I sub Z? How do we know that? Of course, that's what you're here studying engineering for. We do it through using our knowledge of the phenomena of series and parallel resistances, and then figuring out what those are and doing it. And that's what we're going to do to solve this. Now, let's also look at node B, because we know a couple things about node B too. I'm going to just put node B sort of over here so that I can still draw upwards on node B. So there's node B right there. Just like node A, I'll just put A over that and B underneath that. So there's node B, and what is the current that is, you can see that this is flowing out. I sub Z is flowing out. And where's it flowing? It's flowing through this resistor here. Can it go anywhere else? Is there anything else that's coming out of the resistor? No. There's only one line. It's going right through that resistor. So this current right through there, which is I sub Z, is coming down. So that's the same current that's flowing into B, isn't it? So I sub Z is coming down from point A and it's flowing into point B. Now, what else do we know? We know that the current, right, there's nothing between here. So if the current is flowing back into the power source or battery or power supply over there, it's also got to be coming from this direction, doesn't it? So we know that the current is going to be flowing out of B. And how much is that current that's flowing out of B? Well, that's I, right? That's what we called it. We called it I. So that's I, really I total, right? The total thing that's coming out of the power supply and going back in. And then where does this current go? This current flows out of here, and then it flows down here through R5, and then it flows back in this way, doesn't it? So I've got my current coming back into here, and that current is the same current that went out at point A. So I sub W. So we get the other equation right here, which really is pretty much the same, because the current out is going to be I and the current in is I sub Z and IW. So what we really have, if we're summing up the currents that are going in, we've got I sub W plus I sub Z equals I. Same exact equation, at the two different nodes, just summing up the current that's going in there. And of course, I set it up that way because this is not as difficult a problem as you might believe that it is. Now, before we get into solving that, what looks like a very complicated circuit, we've got to go through our understanding of series and parallel resistance addition, right? So we know if we have resistors in series that each one of those is going to add together to give us our total, our equivalent resistance. R1 plus R2 plus R3, right, in series is going to be equal to R equivalent or R total. That's how we add resistors in series. You can see some resistors in series that we've got here. R1 and R2 are in series with one another, aren't they? Yeah. How about R4, R5, and R6? Aren't those in series with one another too? So if we wanted to, we could come up with an equivalent resistance here for that, couldn't we? And if we wanted to, we could come up with an equivalent, just to simplify our circuit, we could come up with an equivalent resistance here too, couldn't we? Does everyone see that? In fact, I'm going to do that. I'm going to do that with our circuit in just a minute through the simplification process of resistances. Now, here's the thing that's the hard part for a lot of students to understand. And that is that if you have, instead of having those in parallel or in a series, if instead you had them in parallel. Now, also I want to say there's no other resistors in this in series, is there? There's just a bunch of resistors here and they're all in parallel, right? I'm going to actually put a fourth resistor in there. And so if this is R1, R1, R2, R3, R4, and I've got all four of those in parallel, then I would say that my equivalent, in fact, I would say that 1 over, yep, here you go. Make sure you write this down. 1 over my equivalent resistance is going to be 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4. And yes, you start to practice using your reciprocal key on your calculator because you're going to need it. And that, right? So this is series, and this is parallel. And so now what we want to do is we want to break down the circuit into what parts are series, what parts are parallel. We want to add up those parts that are in series, add up the parts that are in parallel, and get it all together so that it comes to one resistor, right? So really what we want to do is we want to take that circuit right there. We want to take that circuit right there, and what we want to do first is get it to this circuit right here. So we've got a 100 volt DC power supply, and then we've got one resistor, right? That's what we want to do first. We want to get it down to one total resistance of that circuit that the power supply sees. And how do we do that? Well, the first thing is we want to start to get rid of these series resistors. So we know that a series resistor, two or three or four series resistors in series, we just add those together. So let's draw that first. And I'm going to draw that right here because I'm not going to need all that much room. We're not far from finishing this problem. Now let's just put a line down through there so that we can see that that is separated from the rest of the thing. I'm wondering how to do that, but whatever. I'll put something over here, and so you can see that that's part of that. Anyway, let's do this. So I've got 100 volts DC, and then coming out of there, I've got now one resistor. Right? Instead of two resistors, I'm going to get one resistor because I'm going to take R1 and R2 and add it together. And that's going to give me a 220 ohm resistor. Does everyone see that? All right, so if I'm still going to leave in R3, right? R3 is still there. So R3, we're going to take care of that in a little while. But then I'm going to put in parallel with R3 only one resistor. Now, why am I only putting one resistor there? Because I've got R4, R5, and R6 all in series. So I can replace R4, R5, and R6 all in series with one resistor. So let's do that. So we've got R4, 270. R5 is 330. So that makes 600, right? So R4, R5 give me 600, and R6 is 180, so that gives me 780 ohms. So this is going to be 780 ohms. And I wanted to, R3, you know what R3 is, so I don't really have to put its value in there. You still know that from the original statement of the problem. But now I've got a much simpler circuit, don't I? Right? Why don't I just, I'm just going to circle this circuit. There we go. So we've gone from that circuit up there, that complicated circuit, down to this less complicated circuit. And of course, this is the circuit we want to get to. Oh, I see what you're saying. Hey, you forgot R7. That's right, I did. I forgot R7. Thank God they make resistors like this. So I can just draw it in later. Oh, yeah, okay, but that's fine. Okay, so we still have one, or the equivalent of 1, 2, 3, 4 resistors in there. We want to get it down to 1. So you can see that this resistor here, right, is in series with these two parallel resistors here, which is in series with this R7 here. Now, how do we do the parallel equivalency of this? How do we do the parallel equivalency of R3 and 780 ohms? Well, let's draw our circuit again. We've got our 100 volt power supply here. We've still got our 220 ohm equivalent combination there. But now what we want to do is we want to figure out what R3 and R7. So the equivalent resistance, or 1 over the equivalent resistance, is going to be 1 over 780 ohms plus 1 over R3, which is 680 ohms, right? Now, of course, that's just 1 over. So R equivalent is going to equal, we want to figure what this is, and then we want to take it to the -1, don't we? So that we can, because that's what this is, 1 over this, take it to the -1, and it's going to give me our equivalent. And so what I'm going to do is I'm going to write it out like that, and then we can just put our equivalent down right below it. So just a second. So 0.00, I'm going to actually write it out, 128, that's 1 over 780, plus 0.00147. So those are the two, that's 1 over 780 and 1 over 680. But then, of course, I'm taking that to the -1, aren't I? I want to add those two things together and then take it to the inverse so that I can get R equivalent rather than 1 over R equivalent. If I just added those two things together, that would just give me 1 over R equivalent. So I have to take to reciprocate it to get the correct thing. So just a second. And I get 363. So R equivalent is going to be 363.28. I'm just going to say that's 0.3. All right. So my equivalent is 363.3. We can really say it's 363 So why don't we just, why don't we say it's 363? It's just easier to write it all on here. So we now have this circuit. We've got a 363 ohm resistor, and on the bottom, R7, if you look, is 390 ohm. So now we've got 3 resistors in series, don't we? So if I just wanted to, come up with, I'm going to use another color here. Maybe blue would be a good color if it works. So we really went from here over to here, down to here, right? That's the direction we're going in with the blue as far as simplification. In fact, why don't we write that? How do you spell that? No, I actually am a great speller. Simplification. So the simplification process is, this would have been sort of the first step. This is the second step after we did that equivalent parallel thing. Now what we want to do is go to the third step where we go back to summing up series resistances. And so that's what we've got now. Well, let's not forget our 100 volts DC. So let's draw our last circuit, and that's with the 1 resistor, isn't it? And that's going to be our total resistance. And so 220 and 363, actually, why don't we do 220 and 390? That gives me 610. 610 and 363 gives me 973. 973 ohms. That's the total or equivalent resistance of that circuit. And that's the first thing that you want to work with. The first thing is that we want to find out what is the current that is coming out of that power supply, right? And now we can do it because we know that really what that power supply sees when it's figuring out the current I, it has 100 volts and it sees a 973 ohm resistor, right? So it's 100 volts and it sees a 973 ohm resistor. So that's almost 1,000 ohms, isn't it? And that's what you wanted to always do in your head. You always want to do the calculation at first in your head, and then get an approximation of what it's going to be. And then when you put it into your calculator and your calculator says 10 billion, you'll know your calculator is lying to you. That's right. All calculators are liars, especially if you need it on an exam with 5 minutes to go. That's right. Horrible calculator. So let's look at this then. We've got 100 volts and we've got 973 ohms. What type of current does that give us? And you're saying, well, it's about 100 milliamps, I would think. 100 volts divided by 973 ohms gives us 102.8 milliamps. So let's write that again. I equals 102.8 milliamps. How would I write that? Right? If I was writing it in amps to use in my calculator, it's 0.102, right? 0.1028 amps. You just move the decimal point. 1, 2, 3. See how I do that? 1, 2, 3. Or 1, 2, 3. It's pretty easy. It's so easy, but some people just have never learned that. So I just thought that I'd bring that up and mention it. All right. So you can see that right now, my total current, the current that's coming out of my power supply is going to be 0.1028 amps, or 102.8 milliamps, or 102.8 times 10 to the minus 3 amps. Always write times 10 to the minus 3. Don't ever write E3 or whatever, because that's not universal, whereas times 10 to the minus 3 or times 10 to the 3 is universal. Be the engineer, right? That's what I always like to be, the engineer. Sorry about that. I had to get a sip of water. This is my second lecture today, and I think I'm going to try to do one more. Now, how are we doing on time? Well, we're not doing bad. So what we're doing now, we know that the current is 102.8 milliamps coming out of that. So what are the resistors that we're going to see first? Well, aren't we going to see the resistor R1 first? What's that voltage drop across R1? We know the current's flowing from the 100 volts to whatever this voltage is right there. I'm going to call that spot G. That's right, for Professor Graham. That's spot G. Now at spot G, what is the voltage? The voltage at G equals 100 volts, right? Isn't that what it is on this side up there? That's right. It's 100 volts on this side because it's coming right out of the 100 volt source. So I've got 100 volts here, but what's the voltage here? I don't know. But I know that the voltage drop across R1 is going to be the current going through R1 times the resistance value of R1. So 100 volts minus the current that's flowing through R1, 0.1028 amps. I didn't draw that right, did I? Where's that thing? Yeah, I should have put the parentheses around the I don't know. Can't take me anywhere. Okay. Amps. Yes, nobody can tell there was a thing there. Times the resistance of R1, which is 100 ohms. Okay? Now we know what this is. 100 times this. Well, let's just take that and move it to 1, 2. So isn't it 10.2? So the voltage at G is 100 volts minus 10.28 volts. I think we can all do that in our head, can't we? Yeah, that's 42, right? 42.7? No, of course it's not. It's 89.72 volts, isn't it? So we know what the voltage is at that point. Yep, it's like we're soothsayers, seeing the future, predicting the future accurately 100% of the time because we know math, right? Oh, let's take that blue pen too. So if this is our first simplification, that's our second simplification, then this would be our third simplification, wouldn't it? And that would bring us down to the point that we've got right there. I think what I'm going to do is stop it right there because we're still going to analyze the rest of this circuit. This is really the first of our of actually a few lectures on Kirchoffs laws, but series versus parallel and the manifestation of Kirchoffs laws in the solution to this problem. So we're going to work through this problem and we're going to apply Kirchoffs law to this problem too to see if it all worked out exactly the way that Kirchhoff thought it would. Now that we're getting our thing. So I'm going to leave this here. Of course, I'm going to refer back to this, but you've got good notes. I'm glad you've taken excellent notes. Because you're going to need them. I'm going to refer back to this next time, but I'll be redrawing it up and giving you what the currents and the voltages and stuff were that we've done so far in this problem. It's just that I've got to limit the amount of megabytes per video to about 35 to 40 minutes. So this is coming on a little more than 35. So we're going to handle this in the next lecture.